In this second installment of this lecture, I am going to review how energy is calculated. Now, you really need to have some historical understanding with these calculations or these formulas to really have some meaning behind them, to have them stay with you. So we started with Planck, as we talked about, and he solved the ultraviolet catastrophe by mentioning the oscillators in a black body radiator somehow were quantized, meaning that the frequencies of these springs were fixed, and the energy that they have, remember they moved up and down, when they sprung up and down, charges that go up and down create, when they go up and down, electromagnetic radiation. So when you had a black body radiator, as we talked about, is nothing more than an object that has a cavity in it. Okay, it's black, it absorbs all frequencies, and if light gets inside, it bounces around until it's absorbed. And you heat that to a certain temperature, it'll glow. And it gives off infrared radiation, eventually red. Okay, then we talked about today, white hot. Okay, at certain Kelvin. The temperature is a function of the color you see. And the color you see is due to ions moving. Okay, transistors, or I should say, I'm sorry, transmitters give off electromagnetic radiation by moving up and down. Okay, so this moving molecules up and down as temperature goes up creates light in the form of electromagnetic radiation, and eventually it'll form visible light as we go from infrared. Now, at this point, we had a problem because they thought the light inside would all tend toward ultraviolet radiation. Now, Planck solved this by saying that the springs, the oscillators, okay, all did not spring or move at any particular, at all frequencies. They could, the classical physicists stated that these oscillators or whatever's inside, they didn't know about it, they didn't really have a strong understanding of atoms yet, or electrons or protons or those kind of things. So it was about these something moving inside. They knew that moving charges made electromagnetic radiation, as we talked about. So they figured that these things could spring and move at any energy was possible, okay, and that any motion was possible. So that if you gave this energy, these springs could basically have a resonant frequency of any frequency. So that would mean that this could produce, I don't know, X-rays, deadly X-rays would come out of here. Obviously that did not occur. You don't light a fire and X-rays result because of these springs moving at any frequency and moving toward the higher frequencies. Okay, so to explain this, Planck said that very simply that these oscillators inside only moved according to specific, okay, frequencies, or I should say V. And he said that the energy is equal to some whole number integer times some constant we now call Planck's constant times the frequency. So the energy was directly proportional to the frequency times some kind of constant that gave it some sort of, I could say, whole number variable. And I mean by whole number, I mean we took a frequency, whatever that frequency is, you can't have any particular energy with that frequency, as classical energy, classical physics stated. They said, he said in his work, or at least his work said, that the energy is specific, and what he brought up this word quanta. There's a quanta of energy, meaning the energy, either a whole number integer, this is an n that can equal 1, 2, 3, times that frequency times a constant. That constant's like a stepping stone. As I said in class today, if you take a dimmer switch and you turn a light on, it appears like the light's coming up in intensity like that. And if you zoom in close, in truth, it actually comes up in stepwise fashion. And the stepwise fashion is this bundle or this quanta of energy that we're talking about. And we don't see this stepwise fashion because this number, okay, this Planck's constant, or these numbers are so small. But he introduced the idea that somehow the springs inside were quantized. He didn't do a lot of work in trying to quietly explain. He was basically trying to solve that problem. But he was the first to really introduce the idea that energy has specific energy values. It wasn't a continuous wave, and it really bothered him a lot because of that. because he really was a classical physicist, and he really didn't want to disturb the things that he felt so strongly for. But the only way to solve the problem of how black bodies give off specific energy levels, and specifically how they do not run to an ultraviolet catastrophe or an X-ray catastrophe, was that somehow the energy in these springs or the oscillators, whatever you wanted to call them, of course we know now that the atoms had specific energies only. Therefore, you couldn't turn on a spring until it had enough energy. So lower energy springs gave off infrared. Other energy springs only got turned on when the energy was higher. And since there wasn't an infinite amount of energy, as we see in Boltzmann distribution graphs, only a certain amount of energy, the higher energy levels would only turn on certain springs. So the infinite amount of energy deal falls apart, and he saves the day with his explanation. Now, where do we go from here? Well, Einstein, as we talked about in class, did what? He stated that that not only is this quanta we talked about here through the black body radio important, he applied it to light. He had the photoelectric effect. And what he saw is when he struck light onto a metal, we knew already this phenomenon that sometimes that light did not emit any electrons. No matter how bright you turn the light on, you would think that waves, if they're continuous, if you turn the light on brighter, you have bigger amplitudes. You'd have a bigger wave. A bigger wave at the beach should knock you over. So you turn on the light brighter, that should eject electrons. But electrons only were emitted once we reach something called the threshold frequency, sometimes called a work function. So I knew I drew a red there, but I probably should have drew a blue there. But let's say a red light hits, it doesn't work. Now, how much you increase the intensity, which they thought would increase the size of the wave, right? Whoa, that would knock stuff over. It wouldn't eject the electrons. Only when you hit them with a higher energy light were electrons emitted. And if you increased the brightness, you would emit even more electrons. And the speed in which they were ejected is basically a function of how much extra energy. Well, that's for another day. But in any case, that made Einstein believe, okay, at least his very famous 1905 paper, Einstein believed that light was quantized and its energy is equal to Planck's constant times the frequency, but he explained this equation in terms of per photon. And a photon is nothing more than a particle of light. That's right, he introduced that light acted as a bundle of energy, a packet, so to speak. And this packet of energy was specific to the frequency times, guess what, Planck's constant. So if this packet of energy had enough energy, it could eject it. But if it was made of a photon of a lower light, like a red light, that packet didn't have enough energy. So is the wave-particle duality that he first introduced. And this is the energy formula we do. Now we use this formula as a per photon. Now how is it implies today? Well, Bohr, as we talked about a little bit today, took this idea and said, okay, if light is quantized, has specific energies, then that must mean the atom must be quantized. So if you take the protons in a nucleus, right now we have electrons haphazardly in this empty space. He said electrons existed in specific energy levels. Now what he used was orbits. And he said to go from one energy shell to another takes energy. And this amount of energy to go from here to here was specific. That's right. He started organizing the electrons based on energy levels. And electrons that were closer to the nucleus had lower energy. Electrons that are higher or farther away from the nucleus have higher energy. Now, why is that important? Well, think with me for a second. If I'm an electron close to the nucleus, I'm being controlled by my nucleus. I'm negative, it's positive, and we attract each other by Coulomb's law, differences of charges. Now, if you give this electron that, by the way, low energy, you should know from today, is stable, it's going to stay there unless you do what? Give it energy. Mr. Grodsky's going to lie on the floor with no energy until you move him. Okay, now, what if you give him an exact amount of energy? to go from here to here, it's called a quantum leap, it'll become excited. And when it's excited, it's high energy, and you got it, it's unstable. Mr. Unstable, who has a lot of energy. And things that have a lot of energy, give them off. So this thing doesn't stay in this state very long. It's unstable. It's got too much energy. So it jumps back. And when it jumps back, it gives off energy. And it gives off energy in the form of electromagnetic radiation, a lot of times in the visible region. Today, we saw the red line of the hydrogen atom. And that red line is from an electron jumping from its unstable position back to its stable position. So it absorbed a red photon of a certain frequency to jump up, and then it re-emitted that red photon. So when we look at the electron, the emission spectra of hydrogen, we see it has these four basic lines. Here's a continuous spectrum, and here's the lines that it emits when it jumps back from its excited state. Here's the absorption lines, meaning if I shot white light at it, it uses just this part of the spectrum, just this energy to make the leap forward. Okay, I don't know if I can play this, but I will.
If a high voltage is applied to an element in the gas phase, the element emits light. Using a prism, we can split the light into its component colors. Every element emits a distinct set of colors unique to that element.
And that unique spectrum is telling us something about the electron transitions, in this case, excited from the high energy state farther away from the nucleus to the lower energy state. And every single atom has a unique energy level. That's very important. Okay? And today we saw that red line, that red transition. And you could see that this is what they would emit if they go from the high energy state farther away from the nucleus back, and this is what they absorb when they go back. So if you look at another picture, what Bohr did, again, using the work of Planck and Einstein, said that the electrons, of course, were very, very organized. In order to give off light like we saw today, I had to turn on electricity, and I gave the atom, the hydrogen atom in the tube, enough energy to what? To what? Give off energy, to absorb energy. So that the energy, the electricity I gave it, made the electron that was stable, low energy, Mr. Stable, jump to a high enough energy state as long as it has enough energy. It's an exact leap, nothing in between. It became unstable, and then it jumped back and it released energy. The interesting thing, the red line that we saw from the hydrogen is a leap back, but it had to absorb energy first. So the whole story goes, electrons gain energy, become excited, then they jump back, and when they jump back, okay, which is the second side here, it releases the same amount of energy. And what's quantized is that these electrons exist in discrete, definite energy states, and we can measure that energy from the light given off. Okay, now we're going to use this formula to do these parts of these questions now. All right, I know that was a little bit of review of what we did today, but you have to understand how this all works to make sense of all of this. So this formula that Einstein used, okay, really was born from Planck. And this n number integer, see, Planck didn't understand why there was whole number differences of this, meaning you had frequency times h, and then there was a lot of them, or a little bit of them, and Einstein explained that, well, if you had a certain, let's say, 10 joule photon, you can have a lot of 10 joule photons. Planck didn't understand that they were individual packets of energy. So this number meaning how many photons you have. So this is a per photon question. Now, one photon of light, if it's specific enough, like a red line that we talked about, would be enough to take an electron closer to a nucleus and have it leap to a new shell. It would absorb that energy, and then because it's unstable, and the reason why it can go farther away, because now it has enough energy to overcome the positive pulling force, right? And now it jumps back and gives off that exact same light that it absorbed. So it took a red photon and then it re-emits it, okay? And that's why you have the absorption and the spectrum. So in any case, every one photon of light interacts with one electron only. So that packet is per electron. So in any case, let's deal with it. Number 2, what's the energy of a photon of red light at a wavelength of 655 nanometers? Okay, so we know our formula. E equals hv. We also know that C is equal to lambda times frequency. So those are our two governing equations here that are part of this. We want the energy of a photon of red light. They gave me the wavelength. All right, so if you give me the wavelength, then I can solve for my frequency. If I solve for my frequency, because I know this number is constant, I can plug this in here, and I can do a two-step problem. Or, if I'm really smart, I can combine the formulas. How do I combine them? Watch. So if I'm going to put V here, so right here it's for frequency, which is V. If I rearrange this, frequency is equal to speed of light, all right, over lambda. That's what V equals, or I should say frequency. Okay? I'm going to put that value here. So E equals H times C over lambda. And that's my new equation. This equation just combines these two. Now, if you want to do a two-step problem and solve for the frequency first, find this number and then plug it in here using Planck's constant, be my host. All right, so now we're going to plug it in. So we have our energy equals Planck's constant times speed of light divided by lambda. That's our combined formula. If you want to do it in once or you want to do two steps, be my host. It does not matter to me, but I'm going to combine it. And let's do this. Okay, so Planck's constant, H, that's that incremental step that energy has per wavelength. Okay, that's what Planck came up with. So that's going to be 6.62 times 10 to the negative 34, and that unit is joule seconds. And that is something that you should already know. No, you don't. That's a constant, of course, I'll give that to you. Speed of light is something I'll also give to you, 3.00 times 10 to the 8 meter per second, and that's all over the distance of each wavelength, and they gave me 655 nanometers. Now if I was to put 655 nanometers here, we can see clearly meters and nanometers will not cancel. They love to use nanometers or angstroms to deal with wavelengths of light. So what we're going to have to do, party people, is do a conversion. So, right, our conversion here to meters, 655 nanometers. I want to get rid of nanometers, so nanometers go on the bottom. And we want meter. Now a nanometer, okay, is a billionth of a meter. So it's 10 to the 12, 10 to the 9, okay, 12 will be trillionth, 10 to the 9 nanometers equals 1 meter. Now, this is a bigger unit. This is a billionth of a meter, so it takes a lot of them. So it takes a billion of them, nanometers, to equal 1 meter. So the bigger meter, bigger number, bigger unit, small number, small unit, bigger number, for them to equal each other. Okay, and we cancel our hearts away, and then we divide by essentially a billion. And what we get, party people, is 6.55 times 10 to the negative 7, and you guessed it, meters. Now we're in a unit we could use and put that in here, 6.55 times 10 to the negative 7. I like to use the EE key, not the caret key, as we've talked about before. Meters here, and of course check our units as always. Okay, and what I get is I get 3.03 times 10 to the negative 19. Now, of course, meters go bye-bye, seconds go bye-bye, and I'm left with joules. And that's my energy. Not a large amount, But understand this, party people. This is the energy per packet, per photon, per bundle, as light travels as some sort of particle that's dependent on the frequency times h. Okay? And that little particle bundle is called a photon. So this equation we just found per one photon. So it's not going to be a large amount. All right? So that's that answer. I think on my key I have this written down but not circled, so I feel bad. Now I'm over it. Number 3, we're going to finish this up here with what is the energy of 1 mole of photons at this frequency? So right now I have the wavelength, I have the frequency, I have the speed of light, but I know the formula is very simple. Energy is per photon is equal to Planck's constant times frequency. I already have that frequency. Okay, so at this frequency I solve for what is the wavelength. Okay, so the frequency is given to me. So very simple, Planck's constant, which is 6.62. It's an incremental amount of energy times 10 to the negative 34 joules seconds, and I'm times it by that frequency, 3.85 times 10 to the 14, and that's a per second, right? How many waves per second, a hertz? And that's it. Let's put that in our calculator. All right, I get 2.54 times 10 to the negative 19, and of course seconds go by, and I'm left with joules, and that's the energy per photon of red light. Now, do I have an energy per photon of another light? Yeah, so this red light, and they're very similar, I can see here. They're both red light. This one has a higher energy because of a little bit shorter frequency. All right, higher energy. Let's check that frequency out. The frequency we calculated to be, there's H. Well, we never actually calculated the frequency here. If you did it two-step, you have it, and I bet if you did do it that way, because we combine the formula here, but if you did do it that way, the frequency must be a little bit higher to have a higher energy here than this one was lower energy. Any case, moving forward, last question on this page. The minimum energy needed to remove an electron from potassium metal is 3.7. So that's my energy. Now, for removing one electron, this is the energy per photon. Okay, moving a single electron is always due to one photon. And that's equal to Planck's constant times the frequency. So they gave me the energy to equal 3.7 times 10 to the 19, negative 19, of course, small number, joules. Will photons of frequencies of red light and of blue light trigger the photoelectric effect? If so, what's the maximum kinetic energy of the ejected electrons? Well, remember the photoelectric effect is that phenomenon where we strike light onto metals and we see if electrons are given off. Of course, electrons are held by atoms who are positive, so it's basically bundles of light that are carrying energy, and if there's enough energy per particle of light, per photon, you can separate an electron from the atom. And that's how it works. So will photons, so we're saying this is the minimum amount of light needed to remove an electron. So we have to evaluate the red light's energy compared to the blue light's energy. Notice the blue light is larger in energy. So we compare them, so the energy is 3.7 times 10 to the negative 19, so the times 10 to the negative 19 joules for the photon in question, or I'm sorry, for the energy needed to remove the electron. That's the energy needed to remove the electron, sometimes called the threshold energy. Now, they gave me a frequency of red light, so let's do it in red. Let's be crazy, keep it in red. So the frequency of the red light is 4.3 times 10 to the 14. It's always going to be a positive number because it cycles of wavelengths per second, right? It's a lot of them, 1 over a second. And let's do the red. So they gave me the frequency. Let's let's figure out the energy. So energy, as we talked about before, if I combine it together, is equal to C, okay, and if you look above, I don't want to just say it, energy is equal to Planck's constant times C over V, or you could do what? Solve for the wavelength, okay, or in this case, no, they just gave me the frequency. Sorry, I'm thinking way too hard here. Energy is equal to Planck's constant times the frequency. So let's do that. 6.62 times 10 to the negative 34. Sorry for making things more difficult than I have to be. Seems to be my life sometimes. And then we times it by the frequency. 4.3 times 10 to the 14, 1 over second. Let's go find that energy. And I get 2.85 times 10 to the negative 19, and of course that is an ugly 9. 19, and that's joules. I was thinking joule with a 9. Okay, and the seconds go bye-bye. Okay, let's do the blue light. I'll do it in blue. How about that? E is equal to Planck's constant frequency. 6.62 times 10 to the negative 34 joules seconds. This time the frequency of the blue light has to be higher. Okay, 7.5 times 10 to the 14, 1 over second. Seconds cancel. Let's go find that number. And I get, oops, not that. I get Christmas in July. I get 4.97 times 10 negative 19. So the minimum amount of energy it takes to eject an electron is 3.7 times 10 negative 19. The red light, which is this right here, this equation, has this amount of energy per photon, which is too small. So I don't care how much you turn on the red light, okay? How much you turn on the red light, increase its intensity, more photons, it'll never eject any electrons because each individual packet or bundle of energy or photon doesn't have enough to liberate an electron. But the blue light, each packet of blue light has enough energy that is bigger than the energy needed. So of course, the extra energy, okay, although I didn't cover this for my honors kids, the extra energy, the difference between these two numbers will be the maximum kinetic energy ejected. So once you push off or liberate an electron with this energy, any extra energy that you have gives the electron its kinetic energy. So all you have to do to find the kinetic energy that it could have is you subtract these two numbers. So 4.97, okay, minus 3.7, and they're both to the negative 19, so I can do this. So 4.97 minus 3.7, and that gives me 1.27 times 10 to the negative 19 joules. Since it's kinetic energy, they're already in joules. So that would be the kinetic energy. So the blue light has enough energy to liberate, and the extra energy gives the electron speed. So its kinetic energy, the energy of its motion, okay, is due to the extra energy beyond separating it. Okay? And if you fell apart with number 4 a little bit, that's okay, as long as you've understood these calculations. All right, so that's the end of this lecture. Done enough.